Okay, so this is the fifth part of the chapter, so part 5, basis. Okay, so let's start with the definition. One, definition. Okay, so a basis for a vector space is a sequence of vectors that is linearly independent and that spans the space. So we say a basis is of a vector space is a sequence. That means order matters. So if you have maybe v1, v2 in the first basis, and then for the second basis you have v2, v1, both bases are not the same, okay? Because order matters. So is a sequence of vectors that is linearly independent and that spans the space. That means to show that a set is a basis, we need to check two things. First of all, we need to check linearly independence, and the second thing is to check that it spans the set. That means if we pick any element from the space, sorry, it spans the space. That means if we pick any element from the space, we can write it as a linear combination of the vectors of the basis. Is that okay? So let me continue. Number 2, let's see the definition of standard basis. Okay, so definition of standard basis. So for any Rn, okay, epsilon n, which is equal to 1, 0, 0, 1, 2. Okay, 0, okay, comma, 0, 1, 0, 0. I think, let me get rid of, yeah, I think that's fine like that. Okay. 0, 0, 0, 3, and 1. Okay. This is called the standard or natural basis of Rn. This basis, the set of those vectors, is the standard natural basis for Rn. Okay. Okay. The vectors in this basis are denoted E1, or sometimes in physics we call them IJK, vectors. So those are the standard basis vectors. Let me give you some examples. We have the standard basis for R3, the standard basis for R3 is 1 0 0 0 1 0 0 0 1. In order matters. Let me give you the natural basis for polynomial. Natural basis for polynomial n of n degrees is 1x x squared x to the power of n. So the basis, for example, the basis for P2, basis for P2 is 1x and x squared. This is the natural or standard basis for P2. Now let me give you another note here. The trivial space we have seen so far is the zero vector has only one basis, which is the empty set. If you remember, the linear combination of the empty set is the zero vector, we said. Or the span of the empty set is the zero vector. The trivial space 0 has only one basis, which is the empty set. So let us finish this this part about the basis with the following theorem. Number 3, theorem. The theorem says in any vector space, a subset is a basis if and only if each vector in the space can be expressed or can be written as a linear combination of elements of the subset of the subset in one and only one way. So this theorem also is important to prove if a subset is a basis. Okay, so in any vector space, a subset is a basis if and only if each vector, each element of that space can be written as a linear combination of the elements of the subset in one and only one way. So if we pick any element from the space, there is only one combination of C. Okay, so there is one set of C's, C1, C2, C3, Cn, that we can use to express the element of the space as a function of the element of the basis. So we can write the element of the space as a linear combination of the element of the basis in one and only one way. You will see in the next tutorial. So this this fifth part of the chapter is about the basis, but we have two main concepts to study here. We need to study the basis and the representation of a vector in the basis. So for clarity purposes, I'm going to stop here. Okay, and in the next video, I am going to do the tutorial, some questions about the basis. Then afterward, still in part 4, okay, I will continue with the lecture, which is going to be about the representation, how do you represent a vector of the space in the basis, in a basis of that space. Okay, so I am going to stop here and see you in the next video for some examples. Okay, thanks.